Okay, so again, thanks for introduction and thanks for inviting me for giving this talk. As you said, I mean, my background is really computer vision and lately also machine learning and AI. I'm gonna discuss about things we do at Siemens. So again, the big topic, digital twin. So it's all over the place. I mean, Siemens is nowadays overwhelmed with the digital twin, and I mean there are a lot of aspects to it. And is in previous question and answer session, I mean, has been discussed. I mean, it's very much depends on the use cases. So here you can see two use cases. One is the digital twin of the aircraft, which is a complex machine. And it does not necessarily need to be a reconstruction of the aircraft. I mean, this is designed a model which then can be used for simulation and different things, even without really constructing the model itself from the real physical asset. On the other hand, you can see also the one of the Siemens factories, the most modern Siemens factory, like in Hamburg, where they use it as a playground for a lot of new technologies. And one of these is the digital twin. So you can see, I mean, fancy overlay of the processes and digital representations of the machines on the real image. So one of the definitions, but there are probably many. The digital twin is a virtual representation of a physical asset. I mean, it can be considered as an artifact that integrates data and metadata of this physical asset. And here in the industry, I mean mainly about the sensor data. So there are a lot of sensor data from different machines are coming back and should come back to the actual plant model. And the intention of this is to do the prediction or optimization of the performance along the life cycle. And I want to come back to one very old thing, which actually was done at the lab at TUM, where I joined them. And it was by accident the project also with Siemens. So Siemens Areva had a partnership, and they contacted also us at the TUM to actually do this discrepancy check. So they wanted to know how the as-planned model, as you can see in the upper left corner, so as planned, I mean, how this is actually compared to as built. And when you put them together, I mean, using the methods what we developed, I mean, you can actually see the discrepancy between these two models. And I mean, it is quite old work, but it was a very relevant. I mean, it had nothing to do with the artificial intelligence, but more with the virtual and augmented reality. So one of the new use cases of Siemens are actually, I mean, this use case of the overhead line inspection. So here you can see on the left that this creation of the digital twin is one aspect which is very important, and this is where the computer vision methodology comes into play. But the second aspect is this use of the digital twin. So how do we actually make use of this data which we acquire? I mean, how do we go from these color images to detection of the assets, and then in the end, inventorying of these assets on the 3D models using this 3D geo spatial data. So as I said, the creation of the digital twin is one of the important aspects, and this is where I mean, the computer vision comes into play. So here I wanted to show an example of probably many people know the Bentley systems, and this also partners with Siemens. They're using photogrammetry techniques. They're combining the video images and the static images. In this concrete example, the images from the drone and the images from the high-resolution RGB camera on the ground have been used and combined to build this beautiful model where we have this virtual go through. I mean, the pros of these technologies, they're easy to use. I mean, you can take photos at a close proximity. You can take them from the large space outside using the drones. You can cover the large scale. They have pretty good visual quality. I mean, the models are compact because they are sparse. However, they're not very accurate. I mean, the photogrammetry models, you cannot get, I mean, high accuracy, which is required for some applications. For some applications, this is completely fine, but for some applications, this is not enough. And usually, because these are involving high dimensional nonlinear optimizations, I mean, they're timely to produce. On the other hand, what we worked on and where was completely different use case is this digitalization of the large components from laser scans or from some kind of proprietary scanner, which I'm going to talk about. So we have in Siemens factories these big components like the steam turbines, and you want to reconstruct them at a very, very high precision. So when I say high precision, that means for these 5-meter tall objects, we want to have a tolerance of 1 millimeter. And this is completely other scale, another story we are talking about compared to these photogrammetry-based techniques. So if you use the laser scanners or the phase shift scanners or something similar, you can get really this high accuracy. The laser scanners are everywhere and easy to use. I mean, the cons there that this high accuracy actually results in a high number of 3D data points. I mean, extremely high number of points. Then this big data you are slow to acquire and sometimes and it's really cumbersome processing chain involved. In the end, I want to show the use case of the new modern acquisition platform from a TUM startup, Navis, which actually is combining the cameras and laser scanners. And they built this trolley where they can actually do the 3D reconstruction of the interiors of the buildings. And they allow this Google Street View-like navigation through the digital twin or through this 3D reconstruction. I mean, this is extremely easy to use. I mean, it can scale to large spaces. It provides a high quality, I mean, a reasonable accuracy, I would say, but it is limited to these indoor scenarios on the negative side. Okay, so the first part of the talk, it's going to be dedicated to this one use case of digitalization of the large components. So in Siemens factories, it is important, I mean, very important to have a reasonable and good, precise measurement of these large components because they are constantly put into the milling machine. The milling machine has to take some material from these oversized models as shown in the slide. And then it has to be measured to see how much material is actually taken away compared to the CAD model and then again put into the machine. So this cyclical process is very important of the quality control. And this deviation of the CAD model from the actual model is very important. So at the time when we started the project, they were using photogrammetry markers. I mean, they just paste the markers on this huge model, take a lot of photos, do the optimization, and then they get the precise, accurate positions of these marker positions. But this is not good enough because it takes hours to put these markers, and it's done manually. The second, it's sparse. So you put in just the certain locations. You cannot densely reconstruct the whole thing and have complete assessment of the model. So for us, it was important to build something which is completely markerless. So there are no markers involved. And I mean, benefits of that would be, or building these high quality models would be the reduction of the preparation of the work and time, performance increase, then increase of quality and the cost reductions. So the pipeline goes as follows. In the first line, you can see some example images of these large components. Then in the second line, you can see our proprietary scanner, which we built. It's a phase shift scanner. Compared to the commercial scanners like FARO or Surfacer or something like that, it's much cheaper. The second thing is much faster. You don't need half an hour for one scan like we used FARO for. It is based on phase shift technology and is actually scans in a couple of minutes one side of the object. So this produces these 3D scans, which are shown in the next on the right. And then you need an algorithm which actually puts these scans together. This is where one of the main contributions from our side came. Automatic alignment of these 3D scans without markers. Then we produce this final 3D reconstruction. And then this final 3D reconstruction is compared to the CAD model in order to get actually or measure the deviations of the CAD model in respect to the 3D reconstruction in respect to the CAD model. So here are some examples. Probably my first day at Siemens, and this is the factory in, I guess, Mulheim was there. The scanner is mounted on the crane. I'm just trying to see, doesn't matter. Maybe you can see there is an arrow there where the 3D scanner is this completely like research prototype. Well, afterwards we built actually the tripod, which is easy to manipulate, but at that time it was like just mounted on the crane and we were manipulating, moving it around. And this big white spot on the right image you can see is actually the projected pattern. So what we actually come up with is an algorithm which actually uses the nominal CAD model. So the CAD model in this case, it's available, but this is not exactly the CAD model of the physical object. So the physical object deviates from this CAD model. So it's a proximate representation of the physical world. So, but it is good enough. So what we actually had to do is to bring these scans taken from different viewpoints into the one consistent final reconstruction. So there, it was important to align them to the same coordinate system. There are many techniques you can use, key point matching and things like that. Many of them actually failed because you have symmetries, you have repetitive structures and things like that. So we actually used an advanced object detection techniques where we detected the object into the scans. And by doing that, we actually brought all the scans into the coordinate system, the CAD model. And this is what you can see in the middle between the reconstruction and actual and the scans. And then afterwards, we did a multi-view optimization, so graph-based optimization to register all the scans to each other and actually distribute the errors across the scans. So this actually required no markers to be placed. This is big cost saving, and also it was quite dense. We didn't lose any kind of data, and it had really good automation potential. Okay, so here is just a recap that from the 3D scan of the actual from the actual model. On the lower left, you go to the scans, and then scans get registered, and what you can observe, the high quality details which are captured after the final reconstruction has been. So we didn't stop there. We integrated the whole thing into a so-called Digitalization Workflow. This was an innovation fund, likely financed by the CEO of the company. We involved here other more commercial solutions, but we developed them on our own. So we developed also a marker-based solution We developed also a solution based on the turntable, which uses the positions of the motor, because in some factories these turntables on the milling machines are available. We actually implemented the cloud storage. We also implemented the live capture of the data and visualization there. And we could import everything into the SIEMENS NX software in order to actually do the further processing. Okay, so the second part will be about the AI for these as-built digital twins in industrial use cases. I mean, there are a lot of industrial use cases, but I divided or used two. Here is one, which I already mentioned, the overhead line inspection. And the next one is actually the factory planning. So the current procedure where when the power lines are inspected is actually completely manual, or so to say that there is a team sitting in the helicopter and they are basically flying over these power lines and do the visual inspection. I mean, what they are looking for, when they're looking for these hotspots or bird nests, for example, they are looking if the vegetation penetrated somewhere the lines, if there are some other objects, foreign objects like these balloons on gates hanging on the lines, and they were inspecting also the consistency and the status of some of the important parameters like these aerial markers or ball markers or spacers and the insulators and things like that. So the project, I mean, shortly called SIEMENS-IRO or SIEAERO, I mean, uses the artificial intelligence to revolutionize this overhead line inspection. And the first thing is that the current solutions are really inaccurate, slow, manual, I mean, and really dangerous because they have to really approach very closely to the power lines in order to do the visual assessments. I mean, the SIEAERO is actually a next generation service which allows really highly precise assessments of the power lines. I mean, it's faster. I mean, very automatic, fully integrated. I mean, much safer because you can do the scans from the further distance, and it brings enormous cost efficiency. One part of it is, of course, hardware. So we developed a multi-sensor system, which integrates a lot of different sensors like RGB, UV, ultraviolet, and LiDAR and infrared. And we use the artificial intelligence for detecting the necessary assets and also for inspecting them. Do the cloud storage. And I mean, the safety is another thing which dramatically increased in this application. So when we talk about the sensor data, so we have an RGB cameras, and they're high resolution. They're going to up to 100 megapixels. And there are 5 of such cameras. There is a LiDAR sensor, which provides the 3D data. There is Corona ultraviolet sensors, and there are infrared sensors. I mean, we talk about 100 gigabytes of data per kilometer, and this is really a lot of data to process. But since everything is geolocalized, I mean, this is allowing us to connect all this data and everything what is going to be processed afterwards in this middle part where the artificial intelligence kicks in, like detecting of these isolators or detecting bird nests and things like that. I mean, bringing it to this geolocalized representation of the asset. So here is the close-up view of the hardware. So the whole thing hangs on the helicopter, and it can be used from the pretty far distance. So how the data are processed. I mean, since I said that the data is a combination of is taken from the multiple sensors. I mean, then we can actually use RGB images and put them into the artificial intelligence or deep learning methods to get nice detections of these important components. And then these components get actually consolidated into the 3D geospace, which allows us really to know in 3D where each of these artifacts is actually found. In the following video, you can actually see like the fly through. So first the raw 3D reconstruction from the system, then the semantic segmentation done with the deep learning of the power lines, the poles here, and the vegetation, and then also visualization of the detection of these important parts, which can be seen in the next slide. Like isolators, bird protectors, spacers, and dampers are actually visualized completely in 3D. So this is very important when that comes for the service and the maintenance. So here are some examples also of the components and defects, because we are not just detecting, but we also want to detect something which is some defects which are very, very critical. For example, in these glass isolators, I mean, there is some defect, which is in this picture, I think, very hard to see, especially for someone who is not experienced. I mean, when we zoom in, you can actually see that there is one glass isolator which is broken. So in this small scale, I mean, this requires a specific attention in building a specific AI models in order to detect such use cases. And there are many more. So there are a lot of different classes, I mean, of these insulators and also the dampers. As you can see here, the huge variation of these things to be inventorized and also inspected. Here again, the glass isolators and then some dampers as well. So as a summary for the SIEAERO service in a nutshell, so it integrates the hardware solution, so with this multi-sensor information, and then the smart data analytics. I mean, the storage and the processing is done on the cloud, and then everything is accessible through the web interface. So you can actually do the complete inspection report, maintenance reports, and everything quite easily. And you can have it stored. For the next use case, I mean, the factory planning, I just want to show the two scanners of the Navis. So there is this trolley, and there is another mobile scanner, which is mounted. It's a user-centric, which is actually used to scan the parts of the factories that are not easily accessible by the trolleys, like this, where you cannot pass with the trolley or you have to lift it. For example, important aspect of the Navis technology is that you get a live feedback. Maybe this is not always critical, but I mean, for the yeah, here as you can see, actually the blending of the 3D reconstruction and the scanning process. But this real-time aspect, I think it's sometimes important. So the next example is actually the scan of the Amber factory with the Navis scanner. So this is like a screenshot from the Navis viewer, where you can see actually the interior of the factory, and on the right down you can see actually the entire factory reconstructed. And one of the use cases, I mean, is this factory planning. So I will be skipping some things in this video. So one of the things what they use it for is actually that you can navigate easily, but selecting the different floor, for example, here, and you can actually jump to the the next floor in the factory. And once you are inside, I mean, you can actually simply look at what part of the factory or which machines you're interested. And then, I mean, using the Navisiewer, you can actually just cut part of the scan, like here, this line of the machines. What you do then with it, you can actually import it into the Siemens NX software. Here in the NX, you can already see the 3D model of that part of the factory. And then you can compare the two by importing the point cloud. And then in the end, you can actually align them together and see what is the discrepancy. So that's one of the other things, but also you can then cut parts of the this model and then see how it will look like if you want to replace one machine with some other machine. And this is very important for replanning the factories at the different sites, which are similar, saving enormously the time and the costs. Okay, so as a concluding remark, I mean, I just want to connect the AI at the high level with the asset optimization throughout the life cycle. In the previous example, you saw that, I mean, there was no AI involved, so in the factory planning. So, of course, if we include more sensory information, because every of the machines have a lot of sensors connected, and they constantly provide different kind of measurements. This information can be fed back to the digital twin, and then the optimization can be performed. And this is this loop which happens here. And some of the use cases I've shown: inventory discrepancy check, asset optimization are already on the way. However, one critical thing which we are currently looking at is this reverse engineering, and this is something what not so many people actually did. So we can actually provide the 3D or do the 3D reconstruction of the assets, but for some models we don't have any CAD models. I mean, so we can perform the 3D reconstruction of some old turbine, but we don't know how this is built. And reversely engineering it currently takes days, months, I mean, even a year for a designer engineer to actually build the model made of these geometric primitives. So the AI can help us to actually detect these primitives and also output the steps of the design and how these geometric primitives are put together in order to build this kind of model. The same for the buildings, and we have the reconstructions of the interiors. I mean, we can use powerful models like generative modeling and the reinforcement learning in this case to build the interior plans, to build the entire 3D plans of the factory of the buildings, and also populated with the CAD models. And I mean, building, I don't mean just segmenting or doing the segmentation, but really giving the steps how this is actually brought into life from the designer side. So as a conclusion, I want to say that computer vision contributed significantly into the creation of the digital twins. Then, I mean, keeping this as built and as planned models in sync is very, very important for the asset optimization. And finally, the future is in the AI. And I mean, this is the technology which will drive digital twins toward these goals.